So far, we've dealt with lots of linear objects in this class, and now in this section, we will take care of something quadratic. So a quadratic form on Rn is a function that sends x to x transpose times a times x. So here, well, if you analyze this matrix vector product, well, x transpose a x is a multiplication of 1 by n and n by n and n by 1 matrix. So this will give you eventually a scalar. And here, A has to be a symmetric matrix. So let's look at the example below. So there should be a reason why we call that as a quadratic form. So let's see that from the following example. So suppose that x is given by x1 and x2, and we're going to compute x transpose ax and x transpose bx for a diagonal and b a symmetric matrix. So first of all, x transpose ax equals to x1, x2, and you multiply this to 4, 0, 0, and 3, and you multiply x1 and x2. So the last two equals to, so we have x1 and x2 at the beginning, and it should be 4x1 and 3x2. And if you multiply these two matrices, then you will get 4x1 squared plus 3x2 squared. On the other hand, x transpose bx equals to, well, again, we have x1 and x2, and 3, -2, -2, and 7, and x1 and x2, and calculating the matrix vector product gives you, so x1 and x2 times, I guess we have 3x1 minus 2x2, and -2x1 plus 7x2, and this equals to 3x1 squared minus 2x2 x1 minus 2x1 x2 plus 7x2 squared, and this equals to 3x1 squared minus 4x1 x2 plus 7x2 squared. So the quadratic form, the name really makes sense because so we really get polynomials consisting of quadratic terms. So all the terms are degree 2 things. But there's a pattern with the answer versus the given matrices, like this with the matrix B. So do you see the pattern here? So here you can see that 4 goes to the coefficient for x1 squared, and 3 goes to the coefficient for x2 squared. And at the same time, 3 goes to the coefficient of x1 squared, and 7 goes to the coefficient for x2 squared. And the coefficient of the term that multiplied x1 and x2 crosses over, like -4, that split into two parts and go to the off-diagonal entries like -2 and -2. So by applying the pattern to this example, we can actually find the symmetric matrix A such that Q equals to x transpose times AX. So basically we can build A by, so the diagonal element should correspond to the coefficient for x1 and x2 and x3 squared. So you put 5, 3, and 2 over here. And the cross product terms, x1 and x2, well, we separate this into two parts by dividing the coefficient of x1 and x2 by 2 to put 1, 2 entry and 2, 1 entry. And again, you separate this into 2, that gives you 4, and put that into 2, 3, and 3, 2 entries. So we get 4 here and 4 here, and the rest are zeros. Then if you multiply this by x1, x2, x3 on the left and the right, then you will get Q of x. So here you can see that the matrix A is a symmetric matrix. So we know that Q of x can be written as x transpose A times x, where x transpose is given by x1, x2, and x3, and A is given by 5, -1/2, 0, negative 1 over 2, 3 and 4, 0, 4 and 2, and x is given by x1, x2, and x3. So if you plug in the vector x equals to 1, 0, negative 1, then we get 1, 0, negative 1 times the matrix A, 0, negative 1 over 2, 3 and 4, 0, 4 and 2, and you multiply this to 1, 0, negative 1. So if you calculate this part, then that gives you, so we had 1, 0, negative 1, and this will give us the column vector that equals to 5 and negative 1 over 2 minus 4, and I guess negative 2, and this equals to 5 plus 2, that equals to 7. So you can see from the examples that quadratic forms are easier to use when the corresponding matrix A is diagonal, or in other words, the quadratic form has no cross product terms. Okay, then you might want to ask whether there is a way to make quadratic forms having cross product terms easier. So basically we can achieve that by doing the change of variable method. So basically what we are going to do is we replace x, the vector x, with some other vectors that is given by py equals to x for p an invertible matrix. Then if you plug that to the quadratic form, well, we had q equals to x transpose ax. But now if you plug this into x, then this gives you py transpose a times py. Or if you distribute the transpose, then this gives you y transpose p transpose a py. Or if you regard this as n by n matrix, then we get this times y. So we have A is a symmetric matrix. Then how do you want to choose P? Well, we can choose P an orthogonal matrix such that P transpose AP is diagonal. Basically, we are taking the orthogonal diagonalization for the given symmetric matrix A. So let's look at the following example. So suppose that A is given by this 2 by 2 symmetric matrix, and let's say Q of x equals to x transpose A times x, where the eigenvalues for A is given by 3 and negative 7, and the corresponding eigenvectors are given by v1 and v2, and they are also normal vectors. So then we have, so Q of x equals to x transpose A times x. Well, if you expand this, then we have x1 and x2 times 1, negative 4, and negative 5 times x1 and x2. And then this equals to, so we have x1 squared minus 8 x1 x2 minus 5 x2 squared. And again, these two quantities goes to the coefficient of the square term, and adding these two goes to the cross product term. But if you diagonalize the given matrix orthogonally, then we have P equals to 2 over square root of 5, negative 1 over square root of 5, and 1 over square root of 5, 2 over square root of 5, and D corresponds to the matrix of eigenvalues. So it should be 3, 0, 0, negative 7. Then we have A equals to PDP transpose. Then this gives you the quadratic form x transpose AX. Well, this certainly equals to x transpose times PDP transpose times x. Or if you put the parenthesis over here and there, then this equals to, I guess, P transpose X times D times P transpose X. So if you regard this quantity equals to Y, or in other words, we have P transpose X equals to Y, or X equals to, so if P is orthogonal matrix, then P transpose is the same as the inverse matrix of P. So this gives you P times Y on the right hand side. Then that Y gives you, oops, I forgot to put transpose over here. So we get Y transpose and D times Y. So because we have D equals to the diagonal matrix, we get this equals to 3y1 squared minus 7y2 squared. So in other words, by orthogonally diagonalizing the given matrix, we can get rid of, so we originally had the cross product term like x1 and x2 over here, but this equals to 3y1 squared minus 7y2 squared that doesn't have any y1 and y2 in it. So for the case when A is not diagonal matrix, then we can apply the change of variable to kill the cross product terms by replacing x with p times y, where p is the orthogonal matrix of eigenvectors of A. And theorem 8 summarizes what we have seen above. But here, I want to note that P was in fact a change of coordinate matrix from the eigenbasis to the standard basis. So we can rewrite this as like y equals to, in fact, the b coordinate of the given vector x, where b equals to a set of eigenvectors for the given matrix A. Now, we call columns of P as the principal axis of the quadratic form, and the vector y is the coordinate vector of x relative to the orthonormal basis Rn given by these principal axes. Or in other words, your principal axis has coordinate y1, y2 through yn. We're going to see the geometric meaning of the principal axis pretty soon. But before we do that, let's analyze why change of variable gives you the same quadratic form. So when you change the variable from x to y, you don't actually change the quadratic form. Like for example, if you calculate q of x and q of y in the previous example, then they should be the same. So let's quickly recall the previous example. So we had x1 squared minus 8 x1 x2 minus 5 x2 squared was the same as 3y1 squared minus 7y2 squared. And we had p equals to 2 over square root of 5, 1 over square root of 5, negative 1 over square root of 5, and 2 over square root of 5. And here, if you plug in x equals to 2 and negative 2, then that gives you our vector y equals to, so we had x equals to py over here. So y should be the same as p inverse times x. And this is the same as, well, because p is the orthogonal matrix, p inverse is the transpose of p. So we have 2 over square root of 5, 1 over square root of 5, and negative 1 over square root of 5, and 2 over square root of 5. And you multiply this to 2 and negative 2. And this gives you, this should be 6 over square root of 5 and negative 2 over square root of 5. So q of x, well, if you plug in x on the left hand side over here, then this gives you, I guess, 2 squared minus 8 times 2 times negative 2 minus 5 times negative 2 squared. And this equals to 4, well, I guess plus 32 minus, so 4 times 5 is 20. And this equals to 16. On the other hand, if you plug in y over here, then that gives you q of y equals to 3 times 6 over 5 squared minus 7 times negative 2 over square root of 5 whole squared. And this equals to, I guess, on the numerator, we have 36 times 3, which is 108. And we divide this by 5 minus 4 times 7 is 28 over 5. or this equals to 80 over 5, and this is the same as 16. So we get the same answer. A quadratic form is positive definite if q of x is positive for any non-zero x, and it is negative definite if you get the quadratic form negative for any non-zero vector x, and it is indefinite if q is either positive or negative depending on your input vector x. So if q of x is positive for some x, and if you plug in another vector, then you can potentially get negative value. And the quadratic form is positive semi-definite if it is positive but potentially can equals to 0. So q of x is greater than or equals to 0, and it is negative semi-definite if q of x is less than or equals to 0. So if you have a quadratic form, then we can write that as x transpose times a times x, but you can actually diagonalize because we have a symmetric matrix, and that procedure doesn't change your output value. So what that means is, for example, in R2, q of x equals to x transpose times a times x, but orthogonal diagonalization gives us this quadratic form equals to y transpose d times y. Or if you expand this to the matrix vector product, then we have y1, y2 multiplied to lambda 1, 0, 0, lambda 2, and y1, y2. Or this is the same as lambda 1, y1 squared plus lambda 2, y2 squared. So to have q of x to be positive, or this quantity to be positive, then we need both lambda 1 and lambda 2 has to be positive. So the quadratic form is positive definite if and only if all the eigenvalues are positive. And on the other hand, it is negative if and only if all the eigenvalues are negative. And it is indefinite if and only if the eigenvalues of A has a property that, well, some of them are positive, the others are negative. So this really helps us to see the geometric meaning of the quadratic form. So let's say A to be a 2 by 2 symmetric matrix, and Q is the quadratic form that is defined by x transpose times A times x. Then for a fixed value C, we want to see the geometry or the graph that is defined by this equation. So if you restrict ourselves in R2, then this will give you a quadratic form in two variables. And we already know the answer. So the answers are one of the following. You can either get an ellipse, or a hyperbola, or two intersecting lines, or a single point, or there could be no solutions. And if A is diagonal, then the graph is in standard position, or in other words, the axes are on the x1 and x2 axis. So let's look at the example below to see the graph of the quadratic form. So let's say A is given by this diagonal matrix. Then if you calculate x transpose times A times x, then this gives you x1, x2 times 1 over A squared, 0, and 0 and 1 over B squared, multiplied to x1 and x2. If we know how to distribute everything, I guess we have x1 squared over A squared plus x2 squared over B squared. So for example, so x transpose times ax, the quadratic form equals to 1, gives us x1 squared over A squared plus x2 squared over B squared. Well, this equals to 1, and we already know the answer for this. So this is the equation of the ellipse that looks like this, where A is over here and B is over here. And the principal axes are x1 and x2. And indeed, this graph is in the standard position. On the other hand, if you calculate x transpose times ax for this matrix, then this gives you 1 over a squared times x1 squared minus 1 over b squared times x2 squared. And this equals to 1 gives you a graph of hyperbola. So we have x1 and x2 here. And the graph of the hyperbola is given by this. And we know that the vertex is located at A. And there are two asymptotes. And again, this is in the standard position with principal axes, x1 and x2. On the other hand, if the given matrix is not a diagonal matrix, then the principal axes are y1 and y2 that we can get from the eigenbasis. And in that case, we don't get the graph in the standard position, but as you see below, the graph will be tilted somehow with the principal axis y1 and y2 over here, and y1 and y2 over here. Now, if you don't fix C, or if you allow C to be varying, then we can plot the graph of the quadratic form, like plotting the points x1 and x2 and C. So this axis is x1, and this one is x2, and the vertical axis is C. Then the first picture is, as you can see, we have C is always positive. So this is the picture when you have Q of x has positive definite. But on the other hand, the last picture, we have C is always negative, or in other words, we have Q of x is negative definite. And the third one, this one, if you analyze the function value C, then C can either be positive or can be negative. So this is the case when Q of x is indefinite. And lastly, on the second picture, this is the cylinder along x2 axis, or C can potentially be equals to 0 if you feed the vector or in the direction of x2. So this case is the graph when you have positive semi-definite. And if you take the level curves for all these 3D pictures, then that gives you the 2D pictures that we had before.